This is Dr. Holt. In this video I have a system. It's going to rotate in the XY plane about the Z axis here with an angular speed of 6 radians per second. We want to calculate the rotational energy of the system. With a problem like this, the first thing we want to do is calculate the moment of inertia. And we're talking about the rotational moment of inertia. Now here you have point masses. Now none of these masses are given any dimensions as far as the overall size, so we treat them as point mass. And to do that, we're basically going to do this. We're going to say the inertia about the z-axis is going to equal to the mass times the distance squared. And that's what we're going to be doing here. Let me make the pen just a little bit lighter here. Okay. Alright, so we'll come down here and we'll do the calculation. The moment inertia around the z. And we'll do the 3 first. And to do the 3, we need to know what is the distance from here to the center of this. Now we know the dimension this way is going to be 3, and then we're going to go back up 4 this way because the part is a 6 by 8. And this dimension is going to be the same for each one of these. So to solve that, we will do the 3 first. So that'd be 3 kilograms times, and we're going to do h squared, and this is going to be our h from here to here. And that would be 3 squared plus 4 squared. Now, you think about this too. You could take the square root of that, but you're going to turn around and square it again, so we'll just leave it just like this, which hopefully that makes sense to you, because 3 squared plus 4 squared, that's going to give you 25. You take the square root of that, it's going to give you 5, but then you square it again based upon the equation here. So that'll be our first one, and then we'll go clockwise. We'll go to the 2 kilograms. We have 2 kilograms times 3 squared plus 4 squared plus 4 kilograms times 3 squared plus 4 squared plus 2 kilograms times 3 squared plus 4 squared. When we do that, that gives us a value of 275 kilograms meters squared. And that will be the moment of inertia of that section. And now to find the kinetic energy, all we have to do is we know the kinetic energy. Again, it's going to be 1/2 times I. I'll make it squared. I'm not sure why the thickness of that changed. We'll go back to the lighter. So the kinetic energy about the z-axis is going to be 1/2 times 275 kilograms times meters squared times the angular velocity, which we were given as 6 radians per second. We will square that, and that'll give us a value of 4,950 joules. Pretty simple problem. Oops, do that right. Pretty simple problem. But again, just keep coming back to this, because when you have something rotating about an axis, you're going to go back and use the kinetic energy. It's going to be 1/2 times the moment inertia times the angular velocity squared. In this problem, I have a uniform rod of mass 1.5 kilograms. It's going to be 21 meters long. The rod is pivoted about a horizontal frictionless pin located right here at the end of a thin extension of negligible mass, if I can say that, a distance of 21 meters from the center of mass of the rod, meaning that the center of mass is going to be right approximately about there and approximately right about there. So the distance from here back to the rotational point is going to be 21 meters. Initially, the rod makes an angle of 60 degrees with the horizontal. The rod is released from rest of angle 60 degrees with the horizontal. What is the angular speed of the rod at the instant the rod is in the horizontal position? With this problem here, this is an energy problem to solve. We want to find out what is the potential energy we have in the beginning. So I like to write everything out. So I'll write out my potential energy, gravitation, initial. And I always do this. Again, some of this you don't necessarily have to do, but I like to get in the habit of doing that. Plus my kinetic energy, plus the work done by non-conservative force must equal to the potential energy gravitation at position 1, well actually 1's fine, plus the kinetic energy at 1. And position 1 will be the position right down here at the bottom. So this will be the position 1, and this will be our initial position here. Alright, we know in the beginning we're going to release this, so I'm going to have no kinetic energy here. I have no air friction or anything that's going to be causing any non-conservative work, so we'll take out that. And when I get down to here, what I'll do is I'll let this be my neutral axis. I'll be taking all my gravitational potential right around this line right here. So when I get down to this point here, I will have no gravitational potential either. And the only thing here I will have is kinetic energy. So the initial potential energy, I need to find out what the distance from here is going to be. That's going to be my height. So we can write that as the mass, which will be 1.5 kilograms. Times the value of the gravity, which is 9.8 meters per second squared, times the height, and the height here is going to be 21 from here to here, so that would be 21 meters times the sine of 60 degrees. Again, that's going to give me, what that's going to give me is that distance from here down to here. That's going to be basically my h value. Alright, on the left side of the equation, that's all I'm going to have. When it falls, it's going to have kinetic energy, and again, we know kinetic energy when we rotate is going to be 1/2 times the moment inertia times the angular velocity squared. So I have 1/2 times I times omega squared. What we need to do now is to find the value of I. And we know that we're going to have to use the parallel axis theorem here because we're rotating around this point here. We know that the moment inertia around its own centroid of a very thin rod is going to be 1/12 times its mass times its length squared. We know from the parallel axis theorem that the moment inertia about point O is going to be the moment inertia of about its own center mass, which will be the 1/12 m. 1/12 times mass times length squared, so we'll put that center mass plus the mass times the distance squared. So I'll scroll down here and I'll run the value of I. So I about O would equal to 1/12 of the mass of the rod, which will be 1.5 kilograms times its length, 21 meters squared. And again, that's its own moment inertia around its own pivot point here. Using now parallel axis theorem plus the mass, 1.5 kilograms times the distance from the rotational point squared. Again, that just happens to be 21 meters. That's more of a coincidence than anything else. If I run that value, I believe you'll get 716.625 kilograms meters squared. Right, so that's going to be my moment inertia. All I have to do now is to take out this value right here and replace it with this. So we'll erase this right here. Slide that over. I will slide in the value of I. 716.625 kilograms meters cubed times omega squared. I will run this calculation along here and then divide it by the product of 1/2 times 716.625, and then take the square root of that and I will get omega. And when I do that, I will get omega, angular velocity, will equal to 0.8638 radians per second. Now note, this is not a constant value by any means, because when we start bringing in torque into the equation, the torque value is going to change as this object rotates down. As a result, the angular the angular acceleration is going to be different throughout also. So again, this value here is only at this position number 1. It's not going to be what the value would be initially or anything like that. All right. Best of luck with this. Again, I hope this short video was useful.